This is the sharpest nose cone I've ever made. It's a conical 5-degree half angle constructed from turned and polished aluminum on top of fiberglass biaxial sleeves formed around a mandrel. The enormous cutout inside will let me deploy a payload at apogee. This device is a camera that looks back at the rocket to capture the drogue parachute deployment in slow motion. But this cutout has downsides. It's an aerodynamic mess and a structural weak point, so when the nose cone hits Mach 2, I need it to not collapse. I have an idea for how to fix this, but let's start by getting the fiberglass into the right shape. I started by printing the inner mold in 4 pieces. The base is flared because a flared base is always important. It helps the mold stand upright and it makes sure that it doesn't get stuck. The mold includes a long length of upper section, which couples with the guidance package and houses the camera pod. After the 5-degree taper on top, the nose is largely empty except for a plug which keeps the aluminum nose tip attached. To connect the mold sections, I used CA with a little bit of accelerant. Centering these parts with as little lip as possible is important, as the mold won't come out cleanly if the ridges get stuck. To make the whole mold stronger so I can pull it out, I also ran a 1/4-20 threaded rod up through the center. The tip isn't rounded here like previous nose cones because for this one I decided not to use condoms. If you're new here, I like to use condoms as mold release devices for nose cones, and specifically I've been using these Titan XXL condoms, but I had a lot of trouble getting these to work on my meat rocket. I should be more specific. I had trouble getting these to not break on the inner diameter mold for the nose cone for my rocket, which reached Mach 3 to cook a piece of Wagyu beef. Side note, I bought these from a website called Lucky Bloke, who are very sad to see that I'm not ordering more. I don't really have the heart to tell them that if I'm not making nose cones, there's nothing else I can use this for. This nose cone is much longer than the previous one, so instead of struggling with the condoms, I gave the whole mold a generous coating of super lube to fill the gaps between the ridge layers. Then I brought it outside to give it a coat of E236 mold release for extra protection. This is the same mold release approach I used for the first nose cone I made for the meat rocket, and it didn't work great. I don't think it moved. Uh-oh. I removed all of the infill. I should have used a condom. The key finding with that nose cone is that while Superlube and E236 don't do great on their own, applying just a bit of heat softens the PLA enough to peel it out, and that's my plan here. Like my previous nose cones, I'm using solid composites biaxial weave for this layup. I measured the length to use as a template, then cut a total of 9 layers out for the layup. I don't have hard numbers on this, but 9 is a lot more than I should need for a 4-inch nose cone going Mach 2. There's a huge cutout inside of this nose cone, which means we're losing a lot of strength, so that's why I'm going so overkill with the 9 layers of fiberglass. For epoxy, I'm using Fiberglass System 2000 with the 2060 hardener, so I've got about an hour of time to work with it before it starts hardening. I was real generous with the epoxy pour here, and I should have used 2 smaller cups because filling it to this size made mixing really difficult. So eventually, I just started pouring the epoxy between one cup to the next. This seems to work well enough, so I started the layup. I worked on this 1 layer at a time. I slid the sleeve onto the mold, grabbed some epoxy with my hand, then massaged it in until the fiberglass was soaked. I repeated the process for each sleeve and kept the epoxy application pretty generous, meaning that I'm probably using too much here. A good layup has just enough epoxy, but having too little is a lot worse than having too much. I was so generous that near the last few layers I had to mix a second batch of epoxy since I had run out. Lots of the first batch ended up dripped on the mat or pooled at the bottom, so this process is just very messy. I spent quite a bit of time near the end just massaging the whole layup to make sure we didn't have any bubbles between the layers, and once it looked good, I let it sit for a few days to cure. Once cured, my plan was to use space heater so that I could soften up the PLA, peel it off, and pull it out, and this only kind of worked. I should also say I pulled really hard on this thing to see if I could get it out just naturally, and that did not work at all. I tossed it in front of a space heater to delaminate 1 layer at a time, which sort of worked, but I quickly realized that the way I had printed this mold was working against me. I had printed this mold with infill, and next time I'd probably go with a vase mode print instead of having any infill. The infill here does a great job fighting the ability for the mold to collapse, which would allow it to peel away from the inner wall. Any infill, even if it's not very dense, is pressing that mold against the fiberglass. And in hindsight, this was the case with that first nose cone for the meat rocket as well. It wasn't until I had percussively removed the infill that the mold was able to be peeled out. The PLA did soften like I intended, but it was clear that I was in trouble and this wasn't coming out easily. Now, this thing doesn't really fit in my oven, but it was clear that the space heater wasn't going to cut it, so I set my oven to preheat to 230 degrees Fahrenheit. Now is probably a good time to explain why this is risky. Fiberglass composites have thermal limits. The fiberglass itself can chill at really hot temperatures. I mean, it's literally glass. The epoxy can't. The datasheet for System 2000 says that under the right conditions, this can work up to and beyond 200 degrees Fahrenheit, and its successor, the 2001 series, can go up to 240. Now, PLA should have a glass transition temperature of around 140 Fahrenheit, but it's not going to actually melt until 300, so we can't just melt it out without damaging the epoxy. This thing doesn't really fit in my oven, so I chopped off a bit of the bottom and covered it in aluminum foil just in case something did melt out, whether the PLA or the mold release. Then I tossed all of that in my oven, closed it as much as I could, and covered the top in aluminum foil to try and preserve the heat in there. Starting at 230F in the oven didn't do much, and when I pulled it out, I could only demold some parts. Most of the print was still stuck in there real good, so I figured I had to go hotter. At the risk of damaging the epoxy, I pushed the temp up to 340F and let it sit for longer. This worked a lot better, and I was able to immediately remove the bottom of the mold, as well as the 2 midsections by the 1/4-20 rod. I got it. Oh no! Okay, so there's still some up in the tip. Before dealing with the last upper section, I lopped off more of the bottom and top of the nose cones, and I was sick of getting poked by the fiberglass shards. On the bottom section, you can see the epoxy has darkened a bit here, which means we probably did damage it a bit. It doesn't look too bad. My vibometer says it's probably fine, so we're gonna assume that we have enough margin in here that a slightly cooked epoxy is gonna be okay. For this last mold section, I tossed it in front of a space heater to soften it up, then peeled off the internal edges with the file and hammered it out. This approach worked, but like, barely. There it is.